A simulator can make a cart stop in many ways, but zero speed does not tell us what happened. These 3 lanes begin with identical 1 kilogram carts moving at 2 meters per second. The first cart meets a spring. The second climbs a smooth hill. The third enters a braking pad. We will track each cart together with the object or environment that interacts with it. After each cart first reaches zero speed, which arrangement can recreate the cart's motion without an added motor? Will only the spring return it? Will the spring and the hill return it? Or will all 3 return it? Choose before the carts move.
I expect the spring and the hill to return their carts. I expect the braking pad to keep its cart stopped.
Release all 3 carts. The spring compresses as its cart slows. The hill cart trades speed for height. The brake slows its cart while the pad warms. For 1 instant, all 3 carts have zero speed. Then the spring expands and the hill cart rolls back. The brake cart remains stopped.
The same final speed concealed 3 different physical states. What quantity keeps those histories separate?
We need an account that follows a transfer from motion into configuration or into unresolved internal motion. That account begins with work. Isolate 1 cart and 1 opposing force. While the cart moves, the force acts through a displacement. We call that transfer work. Only the component of force along the displacement contributes to this mechanical transfer. A perpendicular force can turn the velocity without directly changing the speed. Now compare identical carts under the same constant opposing force. One begins at 1 meter per second, and the other begins at 2 meters per second. The faster cart takes twice as long to stop. During the stop, it also has twice the average speed. It therefore moves through 4 times the distance while the same force acts. For constant deceleration, the velocity versus time graph is a triangle. Its width is the stopping time, and its average height is 1/2 of the initial speed. The triangle area gives the stopping distance, the speed squared divided by twice the acceleration magnitude. Multiply that distance by the force magnitude and use force equals mass times acceleration. The acceleration cancels, leaving 1/2 of the mass multiplied by the speed squared. We call this motion account kinetic energy. Positive net work increases it, and negative net work decreases it. The net work on the cart equals its change in kinetic energy. This is not merely a quantity chosen because it happens to be conserved. It measures the work transferred into or out of the cart's resolved motion. Return to the cart and spring. The selected system now includes both of them. As the cart compresses the spring force points against the cart's displacement. The ideal spring force begins at 0 and grows in proportion to the compression. Plot force magnitude against compression. The accumulated work is the area under this line. That area is a triangle with base x and height k times x. Its area is 1/2 of the stiffness multiplied by the compression squared.
Is that energy located inside the cart or inside the spring?
The useful account belongs to the configuration of the selected cart-hand spring system. We call it elastic potential energy. The cart's position relative to the spring determines its value. At maximum compression, the cart's kinetic energy bar reaches 0 while the spring potential bar reaches the original total. Release the spring, and those bars exchange again. In this ideal undamped model, the spring returns the stored work as cart motion. The hill performs the same kind of reversible transfer without a visible spring. As the cart climbs, gravity does negative work on its motion. The kinetic energy bar falls while a gravitational potential bar grows. At the turning point, the cart is momentarily at rest. Gravitational potential energy belongs to the configuration of the cart and Earth system. Near Earth's surface, raising mass m through a height change gives a potential energy change equal to mass times gravitational acceleration times that height change.
Where is 0 gravitational potential energy?
We may choose the bottom of the ramp as 0. We may instead choose a lower reference and add the same constant to every displayed value. The labels change, but the energy difference between the endpoints does not. Motion depends on that difference, not on our bookkeeping origin. Release the cart from the same turning point. Gravity returns the configuration change to kinetic energy as the cart rolls down. The near-surface formula is an approximation for this experiment. The general Newtonian gravitational potential depends on separation from the attracting body. The spring energy graph can answer more than how much energy is stored. Put the cart a positive distance x to the right of its relaxed position so the spring is compressed. The curve gives the potential energy of each possible cart handspring configuration. The marked dot is the configuration we have chosen. At the marked position, a small move to the right raises the potential energy. The local slope is positive, and for an ideal spring it equals k times x. The spring force is the negative of that slope. It therefore points left, back toward lower potential energy and the relaxed configuration. Height gives a second example. Near Earth's surface, gravitational potential energy rises linearly with the cart's height. Its upward slope is m times g. The force is the negative of this slope, so its vertical component is minus m times g and points downward. A curved spring graph and a straight gravity graph give the same instruction. The force points toward lower potential energy. Real systems can change in many directions at once. Imagine a map whose coordinates represent all those possible configurations. This is not a literal hill in the room. Height on the map means potential energy. At one configuration, the gradient is the arrow toward the fastest increase in potential energy. A conservative force points in the opposite direction, toward the fastest decrease. The compact equation records exactly that relationship.
Does every force come from a potential energy landscape?
No, not every force does. Ideal spring forces and Newtonian gravity are conservative, so this rule applies to them. Friction and damping transfer mechanical energy into other degrees of freedom, so they need a separate model. For a spring network, we can add the potential energy of every spring and gravity, then use the downhill direction to compute the conservative force on every node. The same 2-joule motion account reached 3 destinations. The ideal spring stored 2 joules in elastic configuration. The hill stored 2 joules in gravitational configuration. The brake transferred 2 joules into microscopic motion, deformation, and sound that this simple cart state does not resolve. If our ledger includes only resolved mechanical motion, the brake appears to remove energy from that account. If the selected system includes the warmed brake and its internal degrees of freedom, the larger total has not vanished. Conservation statements are therefore inseparable from the system boundary and the modeled forms of energy. Use the model on a new spring. The incoming cart again carries 2 joules of kinetic energy, but the second spring has twice the stiffness. At maximum compression, will the stiffer spring compress by the same distance, by 1/2 of the distance, or by the original distance divided by the square root of 2? Choose before the carts move.
I expect 1/2 of the compression because the spring is twice as stiff.
Both springs must store the same 2 joules at maximum compression. In 1/2 of stiffness times compression squared, doubling stiffness means the compression squared must be halved. The compression itself is therefore divided by the square root of 2, not by 2. Run both carts, and the stiffer spring stops its cart at that predicted position.
If every spring can store and return work, will any network of springs behave like a solid object?
No, that conclusion does not follow. A network stores energy only when its connected lengths change. The next episode asks which connection patterns resist stretch, shear, and bending before a spring network can behave like one soft body.